I hope this will be an interdisciplinary talk and an interdisciplinary discussion, so it's great to see people, not just from comp sci, who of course had to come, but from history and law and all around. So that's really great, because there's lots of different things that interact at this moment in time, this moment in history. And I'm also of the belief that the different academic disciplines, as they've evolved over time, the reason those things exist is largely an artifact of perhaps the complexity of modern knowledge and our need to learn more about those different things. But it shouldn't hide the fact that ultimately there is, I think, an underlying unity of knowledge, even though sometimes it's hard to see because those things are so different. So that's just something of interest to me. Okay, so we'll begin with the trailer. Hopefully the net will cooperate.
This war, we're not winning it. If you speak a word of what I'm about to show you, you will be executed for high treason.
It's beautiful. It's the greatest encryption device in history, and the Germans use it for all communications.
Everyone thinks Enigma is unbreakable.
Let me try, and we'll know for sure.
Mr. Turing, do you know how many died because of it?
I don't.
3, while we've been having this conversation.
Gentlemen, meet Mr. Turing. We're to work together then. I'm afraid these men would only slow me down.
Popular at school, way.
Mathematician's reputation for social skills, right?
You have 6 minutes to complete the task.
Is anything possible? No, it takes me 8. 5 minutes and 34 seconds.
You said to do it in under 6. What is it that we're really doing?
We're going to break an unbreakable Nazi code and win the war.
You know, to pull off this irascible genius routine, one actually has to be a genius.
I'm designing a machine that will allow us to break every message, every day, instantly.
You're going to need all the help you can get, and they are not going to help you if they do not like you.
Have you decrypted a single German message?
You will never understand the importance of what I am creating here.
Our patience has expired.
No!
If you fire Alan, well then you'll have to fire me.
Me too. And me.
You better bloody work.
Alan, you do not have to do this alone.
What are you doing? What's going on?
The Navy thinks that one of us is a Soviet spy.
You've got more secrets than the best of them.
What if I don't fancy her in that way?
Can't tell anyone, Alan. It's illegal.
I'm just a mathematician.
Sometimes it is the people who no one imagines anything of who do the things that no one can imagine.
How could you not want to see that movie? I mean, it's great. I'm just so excited for it. Okay, so let's begin. So this is a talk about Alan Turing and his life and his work. And I said this was going to be an interdisciplinary talk, so I put this up because not many people know that Turing was actually a distance runner and quite an accomplished athlete. So again, trying to take in as much about this place as we can, you know, the life of the mind and in corpore sano and all that. So this is a picture of him in a distance race, and from my understanding is that he was quite good at it. So the first thing I want to do is give people some context for Turing's work before the war and why he was recruited for Bletchley Park. So this is the paper that put him on the map, and we actually read this in 110 Scholars, of course, with a lot of help. These are my 4 degrees take a stab at this. So on computable numbers with an application to the Entscheidungsproblem. Any German speakers in the audience? Okay, so I apologize in advance if for my pronunciation, and thank you for not translating it just yet. We'll get to it. Okay, so just to give you some background, so it's between the wars, and it's 1928. Germany is very big in mathematical learning, mathematical research, and the great mathematician David Hilbert is the head of the department at Göttingen. And he was very interested in solving the crisis of mathematics, which deals with these issues. The idea was basically to put mathematics on a formal, rigorous foundation as opposed to an intuitionist one. And he posed at an international conference in 1928 these three questions on the nature of mathematics. Can we prove that mathematics is consistent, complete, and decidable? Those are three separate questions. So we need to talk about what those mean. Consistent in mathematics means that you can't ever prove a contradiction. This is about not just mathematics, but formal systems, where you have some axioms, some things you start from that are self-evident, you accept them as true, and you have rules of inference, rules of reasoning, and you have some language to describe them. And so the system is consistent if you can never prove a contradiction. Right? And so for example, those three axioms that I put up there, that's an inconsistent system, because from that you could prove both A and not A, for example. So if a system is inconsistent, it's not all that useful, right? Because and we hope that our mathematics is consistent. Hilbert certainly did. If 2 plus 2 is 4 and also not 4, it's not particularly useful. I mean, the universe doesn't care if we have inconsistent mathematics. It's just not particularly useful to us. So a complete system means that if something is true, then you can prove it. That is, you can prove everything that's true. So, and all true statements in the system are provable within the system. And then finally, a system is decidable if there is some mechanical procedure, so I'll have to leave that in quotes for a moment, if there's some way to decide whether any statement in the system is true or false. That is, you could look at it, and a machine, in principle, you turn the crank, and it could say, yes, this theorem, this statement about mathematics is true, or this one is false. So consistency means that if you can prove something, you cannot prove its opposite. Complete means that if it's true, then you can prove it. And decidability means there's what we now call an algorithm for deciding truth, although back then the term algorithm didn't really exist. So I want to just mention the distinction between truth and proof. It's actually very relevant to teaching in computer science today. In fact, for example, in my programming languages class, we're doing some logic programming, and one of the examples that I show is that there's something that is obviously true to a human reader, but the program can't actually prove it. And so we have to explain why. Similarly, in my own research, I'm writing a DNS server, and if you don't know what that is, don't worry about it, but that has provable security properties using an automatic theorem prover. And to try to get all the things to prove about it, you run it, and then you look, and it says, oh, there's a security property, and the system can't prove that it's true. So I have to ask myself, okay, first of all, is it true and the system just can't prove it? Or is it false, heaven forbid? Or is it true and I need to help the theorem prover be able to prove it? So this distinction between truth and proof, which is somewhat sloppy in modern discourse, is actually really important in computing back then and today. So by the end of the 20s, Hilbert believed, and pretty much everybody thought, that the answer to all these three questions was going to be yes. We were going to nail all this down. Mathematics was complete, consistent, and mechanically decidable. We just weren't smart enough. We just hadn't figured that out yet. So along comes Kurt Gödel, at the time a fresh PhD in mathematical logic at Göttingen, and he eventually published, after spending a year or so of his life, this paper, the German paper, and then there's the translation, in which he answered two of Hilbert's three questions, the first two of them. And basically the way that this worked, this is just a simple example of how mathematicians reason about mathematics. They express things in a formal language. If you want to say that 0 is a number, you say it, for example, the number is the the property 0, the property of numbers that 0 is a member. The class of number 0 is a member. If you want to say that every number has a successor that's also a number, you say it that way. To say that m is a prime number means that 1 is less than m, and you can't find an n or a k such that n is between an m and also n times k equals n, blah, blah, blah. This is just so you can be absolutely as clear as possible on how on what you're trying to say. Mathematics isn't normally done this way, but if you're trying to really get things down to their essence, that's how you say it. You could even talk about the infinite. You can say there are infinitely many prime numbers, and that's how you do it. For all n, there exists an m such that blah, blah, blah. Now, what Gödel did was he developed a way of saying, I am not provable. And to actually express it in symbols, well, it's rather complicated. It takes several thousand symbols to actually do it. But if you follow his derivation, if you follow what he did, it's inescapable. In other words, and this is such a profound thing, one of the most profound intellectual results of the 20th century, that if if arithmetic is true, if 1 plus 1 really is true, if plus means what we think it means, and times means what we think it means, and sets are what we think they are, it's just very, very basic things, then the sentence has to be true. That was Gödel's trick. So this sentence, the Gödel sentence, must be true under the most basic assumptions of mathematics. So, if it's complete, then we should be able to prove this statement. But if that has a proof, what does that say about mathematics? It's inconsistent. Ruh-roh. Well, that would be a bad thing. If our mathematics is inconsistent, it's not particularly useful. All right. Once again, if it must be true, so if mathematics is consistent, and we desperately hope that it is, what does that mean? It's incomplete. Yeah, it's incomplete. That's also a row, but a smaller one. Right? Oh well. And not just mathematics, or not even really complicated mathematics, multivariable calculus, but just simple arithmetic. Any math that enables you to talk about simple arithmetic, 1 plus 1 is 2, right, is going to have this property. So Hilbert's 3 questions from 1928, can we prove that math is consistent? Nope. Is it complete? Nope. And in fact, basically any reasonably interesting formal system is going to have true but unprovable statements. And the results of these were formalized in the Gödel incompleteness theorems. So now it's very common, particularly in popular culture, to have some misinterpretations about Gödel results, some of which I've put up there. The truth or falsity of those, some of those statements may be true, some of them may be true, some of them probably clearly are, but they don't follow from Gödel. I try to sum up Gödel's result in something like this: no sufficiently interesting formal system, and most of the systems that we care about are sufficiently complex. There's no sufficiently interesting, sufficiently complex formal system that can prove its own consistency. Nor will we be able to prove all true statements. Right? That is also true. So you need help from outside the system, something you simply accept as being true and self-evident to give you all the rest. So, but that means that mathematicians still have something to do. Right? So presumably that's a good thing. Okay, so there were actually 3 questions about from 1928, and the first 2 Gödel had nailed down. So, but for the decidability question, that's the Entscheidungsproblem, the decision problem. That one still remained unknown, and Turing, a fresh PhD mathematician, took that on. So, but in order to answer that question, we had to get a better handle on what a mechanical procedure was. Remember, the Entscheidungsproblem is the question, is there some mechanical procedure, some algorithm for looking at a statement in mathematics and telling whether or not it's true, unequivocally? Is there some way of doing that? And the notion of a mechanical procedure didn't really exist at the time. That's an insufficiently rigorous concept. That's a fuzzy concept that needed to be nailed down in order for the mathematics to work. So what was needed was a rigorous, pure intellectual model of computation, something that said that everyone agreed on, yeah, this is what computing really is. So this is what he came up with. This is a whimsical figure from the American scientist, but I think it captures it very nicely. Imagine a device with an infinitely long tape. So that tape is obviously not infinitely long, but imagine that it were. And it can read, on the tape are squares, and inside the squares are symbols, arbitrary symbols. They don't have to be 0 and 1. And all the machine can do, so it has all that, and it has some logic where it looks at the tape, it looks at the symbol and says, okay, now I'm here, I read this symbol. If I read this symbol, I do one thing, or I can write one thing. If I read a different symbol, I write something else, and then I can either move to the left, to the right, and then I go into a different state. And the idea state was actually intended to mean state of mind, because a computer at the time was an actual person, because the computers didn't actually exist. A computer was someone who actually computed. So he was actually asking, what is it that a human computer actually does? What is that in this? What does that actually mean? So what he came up with, let's see, here we go. So we actually write Turing machines. We have the firsties in CompSci 426 have recently learned about Turing machines and learned about their fundamental properties. In the scholars class, in the 110 scholars, we actually have them write Turing machines. And we will do, so here is a Turing machine that is computing the number, is printing the number, binary number, 0.0, 0, 1, 0, 1, 1, 0, 1, 1, 1, and it will happily do so until the universe comes to an end, or the battery runs out, or whatever, and so forth. And you notice it's writing symbols and stuff like that. And so the reason why I put this up there is because it's absolutely fascinating. I said this was going to be an interdisciplinary talk. At least for me, and I think for my students as well, you could stare at this in endless fascination because something about your brain says that it's alive in some sense. It's doing something. Even though we know, of course, that it's not. It's just a computer. And maybe if I'll can speed it up a little. And so it's producing this number, which would sort of intuitively, subconsciously seems to require some sort of intelligence. But of course, we know that it's not. What is going on here is that I think the answer comes from evolutionary psychology. It's my understanding that the human mind has in it certain subsystem that's designed to detect intelligence or to detect agency in other living things or in other things. And you can imagine such a system would have survival value. There's a lot of reasons why it's important to detect agency in mind. It's also in other things and also enables us to be empathetic. But that intuition was formed hundreds of thousands of years ago. And when we develop things that are able to do stuff like this, our intuition backfires because we mistakenly equate, I think, intelligence, which is the ability, I would argue, to move symbols around, with consciousness. And this is, I would argue, not conscious and not self-aware, but I think it's showing some degree of intelligence. That's my opinion. So when the first mechanical computing devices came along, for example, when Charles Babbage invented his difference engine, people were saying, wow, you've got this machine that can evaluate polynomials. Only human beings could evaluate polynomials beforehand. We assumed that that's something that required conscious thought. And when you can do it mechanically just by turning gears, people's intuitions got all messed up. And so this is really where the field of artificial intelligence comes from. And the history of artificial intelligence, in some senses, results from this confusion of consciousness and intelligence. Once a computer does it, anyone who does AI research will get this reaction. Once you get a computer to do it, then the reaction, oh, well, that's obviously not intelligent. There used to be, if someone could get a computer to play chess, that would mean that it was intelligent. Well, the best chess players in the world are now computers, but no one, at least in the popular vernacular, thinks that computers are intelligent. We give assignments in 359, the programming language class. I give an assignment called Calculus in 3 weeks. First, Math 141 in 3 weeks. They write a program that can calculate virtually any derivative, which you'd think used to require intelligence, but no, you're just moving symbols around. So we're going to come back to this because Turing is a big pioneer in the field of artificial intelligence, but I wanted to at least just draw the connection that I thought was interesting. And so this is still going strong. We'll mercifully stop it. So this is actually the machine that we just ran from Turing's original paper, where he describes this model of computation. The typewriting stuff, the notes on the left and right are my annotations that I give so that the 4 degrees can work on it, because Turing's writing is very dense with lots of big German Gothic fonts, and it's hard to keep everything straight. But that's what it is. Okay, so it's legitimate to ask, and Turing asks, what can this thing do? And you might think that really not all that much. It can read and write symbols, and it can move things around, and that's pretty much it. But it turns out, if it can read and write symbols, then it can copy them. It can recognize that this string of symbols says this thing, and this doesn't. This is a string of symbols that says something else. If it can copy, then it can add, right? It can count, and it can add. And if it can add, then it can multiply. And if it can multiply, and you can keep going on and on and on, and you build up more and more of this power, as long as you don't care about how long it takes. As far as Turing was concerned, as a mathematician, the only thing that he cared about is would it eventually stop or would it go on forever? Right? It's a standard mathematical joke. The problem is finite and therefore trivial. Right? They're only, whether it's a billion or a quintillion or 30, they don't care. All they care is if it's infinite, then maybe it's interesting, and if it's not, then it's trivial. It's discrete mathematics, and nobody cares about it. But the consensus is that computing is what this thing can do, as long as you don't care about time. It's not something that you can prove because the definition of computing is sort of is fuzzy and always will be. But there's other different models of computation that also came out, and Turing was able to show that they're all equivalent. And so that's pretty strong evidence. This is really whatever that thing can do is exactly what this thing can do if you give it enough time and enough tape, enough memory. So is there anything it can't do? Well, it turns out, you might ask, well, what kind of numbers can be computed? It turns out the impossibly huge majority of numbers can't be computed. For those of you who are mathematically inclined, it's the difference between the cardinality of all of naught and all of one. And if you don't know what that is, what that means, again, it doesn't matter. The point is that the huge number of most numbers can't be computed at all. But that's okay, lots of useful ones can. Fortunately, we can compute e and pi and lots of really useful numbers. But it turns out that you can't make a Turing machine that will read a description of a Turing machine, another Turing machine, and tell whether or not it will stop. So Turing's asking the question, is there some fundamental limit on what these things can and can't do? And the classic way that you do it is, that he proves it, is through a contradiction. If there were such a machine, then you could modify it so that it would run forever if its input machine would stop, and vice versa. Then you ask, so you have a machine that will run forever if its input would stop, and vice versa. So then what happens if you feed it itself? The snake eats its own tail. And so if this new machine would stop, then it must run forever. Or if it would run forever, then it has to stop. So that's a 1-minute introduction into a topic that we actually used to teach back at Comp Sci 110 to all the 4 degrees back in the day. We dropped that like a hot potato. But we do talk about it in Scholars. So basically, the conclusion is there is no such machine. Does that sound familiar? Hopefully it should. Turing says in the introduction to his paper that conclusions are reached which are superficially similar to those of Gödel. So Turing was able to show that the non-existence of a solution, the unsolvability of this problem, was equivalent to a negative answer to the Entscheidungs problem. So that's really what he was trying to do. He didn't set out to invent computing. He only invented this model as a means to have solved this important but relatively obscure mathematical question. But in doing so, he opened the door to this whole new human intellectual endeavor. So there were 3 questions from 1928. Gödel nailed the first 2, and Hilbert said no to the third one. Hilbert died during the war, during World War II, being aware of all these results, but presumably never responding to them. Any of the German speakers translate Hilbert's epitaph? We must know, we will know. Yeah. So he died still believing, apparently, or at least not enough to change his epitaph, that the answers to his question, that somehow these authors were wrong. But at least that was his hope. But turns out no. Okay, so this is the paper that put Turing on the map. So this is 1937, right before the war, and Turing has nailed down one of the big 3 questions that everybody wanted to know about. Okay, so let's go forward about 50 years. Hugh Whitemore has written a play called Breaking the Code based on a book about Turing. Derek Jacobi stars as Turing. Any Roman history fans? Anybody remember Derek Jacobi? Of I, Claudius, yeah. And Derek probably was too. We were such geeks in high school, we would like watch I, Claudius on PBS as soon as the new episodes came out. Right, exactly, yeah. There was a Broadway production that was made of it. It got 3 Tony nominations. In 1996, the BBC took a stab at it, still starring Jacobi, even though he was about 30 years older than Turing at the time. So let's roll tape. So this is the scene now. So after the war breaks out, The code breakers, so the government starts up the government code and cipher school, and they are looking for certain kinds of people, mathematicians, puzzle solvers, crossword puzzle people, et cetera, to come and work on this top secret project to do code breaking. This is so Turing was recruited. This is his interview, a dramatization of his interview at Bletchley Park, which is where the code breaking happened.
I've been furnished with some details of your work, Mr. Turing, most of which I have to tell you I find almost totally incomprehensible.
It's hardly surprising.
I used to be rather good at...
Turing was very dry, very droll.
But this is, well, baffling. For instance, this thing here. On computable numbers with an application to the Entscheidung problem.
Which you all now know about.
Tell me something about it. Well, anything. A few words of explanation, in general terms.
A few words of explanation.
Yeah,
In general terms.
impossible.
It's about right and wrong. In general terms. It's a technical paper, it's about mathematical logic, but it's also about the difficulty of telling right from wrong.
Really means true from false. It's not a moral question, it's a mathematical truth and falsehood.
Well, we always know what is right and what is wrong. Not so, not anymore. It's a problem that's occupied mathematicians for 40 or 50 years. I mean, how do you tell right from wrong? Yeah, Bertrand Russell's written an immense book on the subject, his Principia Mathematica. His idea was to break down all mathematical concepts and arguments into little pieces and then show that they could be derived from pure logic. Well, it didn't quite work out that way, and after many years of intensive work, all he was able to do was to show that it's terribly difficult to do anything of the kind. But it was an important book, important and influential. It influenced both David Hilbert and Kurt Gödel. It's rather like what physicists call splitting the atom. As analyzing the physical atom has led to the discovery of a new kind of physics, so the attempt to analyze these mathematical atoms has led to a new kind of mathematics. David Hilbert took the whole thing a stage further. I don't suppose his name means much to you, if anything, to you. No, well, there you are, you see. It's the way of the world. People never seem to hear about the really great mathematicians. But Hilbert looked at the problem from a completely different angle. He said if we are to have any fundamental system for mathematics, like the one Russell was trying to work out, then it must satisfy three basic requirements: consistency, completeness, and decidability. Now, consistency means that you won't ever get a contradiction in your own system. In other words, you'll never be able to follow the rules of your system and end up showing that 2 and 2 make 5. Completeness means that if any statement is true, there must be some way of proving it by using the rules of your system. And decidability means that there must exist some method, some definite procedure or test which can be applied to any given mathematical assertion and which will decide whether or not that assertion is provable. Now, Hilbert thought this perfectly reasonable set of requirements to impose, but within a few years, Kurt Gödel showed that no system for mathematics could be both consistent and complete. And he did this by constructing a mathematical assertion which said, in effect, this assertion cannot be proved. Classic paradox. This assertion cannot be proved. Well, either it can or it can't. If it can be proved, we have a contradiction. And the system is inconsistent. If it cannot be proved, then the assertion is true. But it can't be proved, which means the system is incomplete. Thus, mathematics is either inconsistent or it's incomplete. It's a beautiful theory. It's quite beautiful. I think Gödel's theorem is the most beautiful thing I know.
Love that one.
But
who says we don't appreciate beauty?
Decidability
We don't appreciate art.
Now, Hilbert, as I said, had taught that there should be one single, clearly defined method for deciding whether or not mathematical assertions were provable. The decision problem, he called it. The Entscheidungsproblem problem. Now, in my book on computable numbers, I wanted to show that no one method can work for all questions. Solving mathematical problems requires an infinite supply of new ideas.
That's a bit of dramatic license. It's not doesn't come out from the paper, at least in my reading.
I needed to examine the provability of mathematical assertions, past, present, and future. I mean, how on earth where's it going to be done? But one word gave me a clue. People have been talking about a mechanical process that could be applied mechanically to solving mathematical problems without requiring any human intervention or ingenuity. Machine! That was the crucial word. I conceived the idea of a machine. A Turing machine which will be able
And
to...
he did not call it that. He was far too modest. He would never have called it that.
It would read mathematical assertion and then arrive at a verdict as to whether or not that assertion were provable. And with this concept, I was able to show that Hilbert was wrong. My idea worked.
Yeah, see. Well, I don't, but I see something.
But you all do. You all see. Right?
The originality you're seeking is clearly remarkable. And I'm sure you'll make an invaluable member of our team. Group, call it what you will.
Okay, so that's the end of part one. This is intermission to give me some time. Let's go out to the lobby. Let's go to the lobby. To transform to Enigma Man. Now I know you all want a shirt like this, and you're wondering how you can get one. Right? So just ask the internet. They'll be more than happy to tell you, because of course everything is on the internet. Okay, so part two. So that's sort of sets the stage for Turing's arrival at Bletchley Park. Why was he recruited? What had he done? And we'll get perhaps to what some of the challenges were. So first of all, what is Bletchley Park and where is it? Well, of course, we'll ask the internet for that as well. Yeah, I don't believe you. I bet I fixed that. There we go. Okay, so where is Bletchley Park? Well, there's Usafa. And Bletchley Park. So we'll fly across the ocean. And we'll come down just a bit north of London into a mansion, a very lovely and very secret location where the cryptographers for World War II hung out. And their job was to break Enigma, right? The Enigma machine, which was the encryption device originally invented for banking by Arthur Scherbius in the 1920s and adopted and improved by the Germans, used by all the German military forces for their communications. So how does it work? So it's easier. We have an Enigma here, and later on we'll be able to like mess around with it, do stuff with it. But it's easier to see if you use any of the 80 billion simulators that are out there. So the Enigma works by you set the wheels to a particular setting. In this case, so these wheels actually have, each wheel has 26 positions with different letters. You set them to something, and then the message that you want to encrypt, for example, if you want to encrypt the word attack, you type A, and that gets encrypted to C, so somebody would write that down. T gets encrypted to G, so someone would write that down. T, the same letter encrypts to different things. That's interesting. How does that work? So let's talk about that. So then someone writes down the M, and then the A goes to C again, and then the C goes to K, and the K then goes to S. So someone would write, the lamps that lit up were known as the ciphertext in the jargon. That in turn would get sent off to a radio operator who would send that out in Morse code. under the assumption that the British were listening, and of course they were, but all they would hear would be the junk, would be the seemingly random settings, random strings of characters. So we'll get to decryption in a second. So notice there are these things called rotors with 26 positions, and inside the rotor, you'd have a circle of letters around here. A wire would go in here, and it would come out some other side. And if you imagine, you could take apart a rotor and see it like this with the inputs at the top, so it's a circle with 26 inputs in a circle like this and 26 outputs in a circle like that. If you were to take it apart inside and the rotor happened to be wired like that, you can imagine it, so it will implement a substitution cipher. That is, the B would come in and it would come out at slot Y and so forth. So what is a substitution cipher? Well, it's a crypto quiz, something like this, where you have, this is something that, it's like something you might see in the Sunday paper, even the regular paper, where each letter stands for some other letter, and the idea is for you to figure out, that's the ciphertext, and you're supposed to figure out the plain text. How do you break these? Common letters, yeah, you look for, if a ciphertext letter appears a lot, it's probably, for an English plain text, it's probably what? Probably a vowel, probably an E or A, and actually the way that you remember, it's Etaon Sherdlu, E-T-A-O-N, and then R-I-S-H, or maybe it depends on how you do it, but that's the rule. So these ciphers are not particularly difficult to break. Okay, now if you put them together, like they are in the Enigma machine, if you put them next to each other, all you get is just another substitution cipher. So each of the wheels would be wired differently inside, but if you put them together, or you put 3 or 4 or 80 of them, you still get just another substitution cipher. So what's the big deal? Well, as some of you may have noticed, or you've seen from here, with each time you push a key, the rotors rotate, right? Go figure, that's why they're rotors. So what happens is when you do your first key press, for example, if the rotor were wired like that, then B would go to H. Then when you rotate, so that's it's as if the wiring rotated this way, that's the same as the letters rotating this way, which is much easier to do in PowerPoint, so that's what I did. Then B now encrypts to D, and you'll see this. If you push the same letter multiple times, it gets encrypted to something different. And if you do it enough times, it might encrypt back to D again, but the point is that the same letter can encrypt to different things. Because with each tick, you're doing a different substitution cipher. Oh, very nasty, very clever, depending, I guess, on how you look at it. When the rightmost rotor rolls around at most 26 positions, then the middle rotor advances 1 tick. And then it does it again. So you think of it, I was going to say a car odometer, now I have to say an old-fashioned car odometer. So I don't know how many people even remember that there are actually physically separate circles with numbers on them as opposed to the digital thing. Now I say at most when it rotates around because the rotors actually have notches at different spots to determine when it kicks over. That's to make it hard, right? So that's something else you have to think about. Now, as the current flows through the rotors, when it gets, so you have 1, 2, 3, or however many it goes through, and then when it gets to one side of it, and you'll see this when we take this apart, it gets to something, to a rotor, a fixed rotor that doesn't rotate. It's called the reflector. And all the contacts in the reflector, so this is just a ring with 26 contacts around it, and they're all wired together in pairs. So it comes in over here, and it might come out down there. Another one might come over here and come out over there. So that's called the reflector. So now we're looking from top to bottom. So if you have 3 rotors at any one time, so A would get encrypted, and it would go through the rotor and come out this way, and then it goes down to the reflector, bounces around, and comes back out like that. So this reflector gives 2 important properties to the machine. One of which makes it very easy to use, the other which makes it less secure. Now, those of you in my line of work will hardly find this surprising. It's as if there's some sort of trade-off between convenience and security, right? Who knew, right? So, and we see this all the time. So what are the 2 properties that the reflector actually gives? If I take the arrows away, you see it. And this is non-comp sci people. So comp sci's stay quiet, because you probably know the answer. Like a what? What about it? What do you mean by scaling? I don't think so, but good for you for having an idea. Any idea, even an incorrect one, is better than none, which apparently is what everybody else had. So good for you. Good, it's symmetric. If A encrypts to D, then D must encrypt to A. So it's symmetric. All right, that's the ease of use property, and we'll see that in a second. Okay, so what does it mean? So in particular, what does this mean for Enigma operators? It's a symmetric device, which means that the same machine and the same settings of the rotors are used, can be used, and must be used for encryption and decryption. So if you agree, and you can keep it secret on the initial configuration of the machine, then you type in the plain text and the ciphertext comes out. You type in the ciphertext and the plain text comes out. So it's a symmetric encryption device for those in the crypto field. There's one other one. This is the property that makes it less secure, so it's bad for the Germans and it's good for the Brits. This one may be a little harder to see. So here's your first hint. So each of the rotors implements a substitution cipher. I think the math department had another talk. I was hoping I'd get someone from the math in here. But each one of these, each cipher is a permutation of 26 letters. It's members of the group, which is a specific mathematical structure. It's members of group S26. So that isn't going to help anybody, but that might. What else can we say? What must be true? There's a particular property. Or what can't be true of encryption of a particular letter? Yeah, Jim says it's right. No letter can encrypt to itself, because it might encrypt to itself as it gets through these three rotors. That's certainly possible. But because each of the rotors are as a substitution cipher, there's only one path, one input and one output. And because the reflector sends it back a different way, no letter can encrypt to itself. That turns out to be a gold mine for code breakers. Okay, so I already said this. The other consequence then is that Enigma is not a perfect encryption device. And this isn't just because the fact that no letter can encrypt to itself. So the jargon in crypto is that the entropy of the plain text given the ciphertext is less than the entropy of the plain text itself. If you see the ciphertext, however much of it you can see, you have some information, not much, but some about the plain text. And that's a good thing. Any form of information at all for code breakers is a good thing. Okay, so to give you some idea of how hard Enigma is to break, suppose that you have, you're at Bletchley Park, you're at a listening station somewhere on the channel or whatever, and you intercept this Morse code. It turns into these letters. So you might ask, all right, so how many Enigma settings could have produced it? Well, the shorter answer is a lot. So an eroder in principle could have up to 26 factorial wirings. If you don't know what a factorial is, don't worry about it, but it's that number. So that's a lot. And there are three, let's assume we've got three rotors, and so you have all those, and let's assume that no two are the same. So you have the first, you pick the first one, you have 26 factorial, and you subtract one, but it doesn't really matter. And then two, so you multiply all those together, you get that. The rotors could be in any of 26 starting positions, so there are 26 cubed of those, possibly. Where's the rollover notch? Well, you got 26 different possibilities for that. So the third notch doesn't matter because that one doesn't affect anything, but you have 26 squared for that. How about for the reflector? Well, you got 25 choices for the first one, you got 23 for the next, and so on, so you have that many. But there's more. Enigma operators are standing by. If you order now, thank you. If you order now, you'll get the plug board. This is a special feature added by the Germans to Scherbius's original machine to make this go. And here's how it works. Part of the configuration of the machine involves setting between none or up to 13 steckers or cables. These things here, these little two ends here and here, between a pair of letters for each one. And the effect of that is to swap the letters before they, if R and A are swapped on here, you press an R, but the A is actually what goes into the machine and vice versa. How do you deal with that? Well, let's suppose the setting of the day requires 3 cables. Then you have, so you'll have P equals 3 cables, so you'll need 6 sockets to use them. And let's say that those 6 happen to be these 6 letters here. So you pick one, they're all going to be filled, so it doesn't matter what the first one you pick. You've got 5 choices remaining. So I'll just pick one, and again, they're all going to be filled, so it doesn't matter. Then you've got 3 choices remaining for the second one, and then for the last one, you only have 1. Okay, so that's, and they're all filled up. So for P in general, that's the formula for how many, and that's just for one group of 2P sockets. You have 26 take 2P, groups of 2P, and don't worry about that if you don't know what that means. Sum all that up, and you get that. It's the greatest encryption device in history. But there's more. The operators didn't have just 3 rotors to choose from. Later on in the Navy, for example, they had 5 or 6 or 7. And part of the settings of the machine was what order they would go in, which 3, and what order they would go in. So if N is the number of rotors you have to pick, then that's the symbol for that. And finally, which of the things stand for A and B and C? If you take these out, you can actually, the ring of letters actually rotates in one of 26 different positions. And that's the Ringstellen, the ring setting. So those can start anywhere. So this is a code sheet from the Enigma. This is what an Enigma operator would see. They were, the tog, of course, is date, so you'd start and you'd go backwards. Or you'd go from the bottom and you tear them off each time. So for example, if the date of the month was the 30th, or the 30th of June, you would use rotors number 5, 3, and 1 in that order. You'd set the rings, the Ringstellen to those particular settings. The Steckerverbindungen, my apologies. That's the settings for the cables, where what letters would be connected with each pair. And then the Kengruppen we'll get to in a second. Fun, fun, fun. Question? Okay, all right. So, and part of the thing, remember, this complicated procedure, a lot of this was done by young, sometimes untrained or poorly trained radio operators in the enlisted corps. And some of them perhaps may have been conscripts. And that turns out to be of help. Okay, so when all is said and done, in theory, you have that many machine settings. That's a lot. That's a lot. All right, so it's legitimate to ask, and so how in the world was Enigma actually broken? And it was broken to considerable effect. So it turns out there weren't actually 26 factorial rotors to choose from. There are only a few that were actually manufactured by the German Cipher Bureau, because those were all then distributed in the field, so you need to have a fixed set to choose from. So of course, the wiring of those rotors was a closely guarded secret, but it was eventually discovered through various means. By the time you work through all those kind of things, you get down to about 1/6 of the number of atoms in a mole of stuff. So still a lot, and still an intimidating problem. So the Enigma was broken through the human side of things, through the things that I mentioned up there, through human frailty, human effort, human courage. So there's some great espionage, some great stories that our history colleagues, I'm sure, know very well about espionage and intel to break Enigma. And there's some things that I guess I'll talk about. Human error was big, in that the protocols used to use the Enigma weren't always followed. And human effort, in particular, I talk about the mathematicians, in particular, talk about the Poles. Hans Thilo Schmidt had a brother in the German army. Who managed to get him a job in the Cipher Bureau. He sold the Enigma operating procedures, and his job was also to get rid of old Enigma keys when they were done. He sold those secrets for a decent amount of money. He apparently was jealous of his brother and ran into some hard times. He initially tried to sell, and this was between the wars, to I think the French and the Brits, who were not interested, interestingly. But the Poles, as you might imagine, were very receptive to the idea. The Poles, since they shared a border with Germany, they were pretty clear as to what was coming down. And they were very, very interested. And as a result, the first breaks for Enigma were actually done by the Polish mathematicians, in particular by this guy. The Poles are unsung heroes, often unsung heroes of Enigma. But the Bletchley Park and the Bletchley Park mathematicians built extensively on the work of the Poles. So I apologize for, believe it or not, I actually cut the talk, but I apologize to people who need to leave for their 1:30 class or 1:30 obligation. Please feel free to do so at any time. There are actually, so we can cut to, there's some living history that's going on here. This guy, find him here, this guy actually boarded a U-boat that was actually raised to the surface by a hit, a perfectly timed, perfectly gauged depth charge, actually boarded a U-boat and made off with an Enigma machine and the code books. And he was interviewed when the film, the U-110, there was some, I forget exactly what it was, there was some big studio motion picture about capturing a U-boat, and he was the guy who did it. So I thought that was pretty cool. Okay, so imagine that, so let's talk about human error and the protocols for using Enigma. Imagine that you are gathering intel from Bletchley Park, and you've got listening stations all over the continent, and this is your daily traffic for the day. You've got hundreds of messages, all of which were used for this, were set with the same daily key. All of which were sent with this. So it's all nonsense, but you've got that. What can you do with, what do you know about the first letter of every message? Maybe, maybe not. In this case, they happen to be different, but they don't have to be. In fact, there's hundreds of them. Right. All right, so you also know that the first letter of the first message is not C, and the second one is not J, and so on. What else do you know? They're all encoded the same way, right? So that, what can you do then? This is all, they're all set with one substitution cipher. So you could do frequency analysis on it. So the Germans knew this, they weren't stupid. So the point is you had to do something else. You can't simply set your machine to the day key and then type, because it will be vulnerable. It's tedious, but you can do it. The first message, the first letter, this was set with one substitution cipher, this was set with another, this was set with another, and so forth. And there's 26 cubed different substitution ciphers before it repeats. For those of you who are crypto people, Enigma is essentially a Vigenère cipher with a very, very long key. That's how that works out. So what you actually did, and similarly then for the second letter, that's all encoded with a different substitution cipher, so you can do that. So the encryption protocol, and there were different ones, but this is basically what you would do. The protocol for Enigma use was you'd set the machine to the day key. Presumably that's secret. If the Allies have the day key, and sometimes they did. Sometimes they'd capture a book. The keys were changed every month. Sometimes they'd capture a code book for a month or at the end of a month, and they were golden for that day. Sometimes. But so what you would do is you would actually send a random, so that right away ought to give you pause, because having human beings pick random things is not a good idea. So you're supposed to, you pick some random letter, you actually send that in the clear. You don't use that in Enigma, you just put it all out there. Presumably the Allies don't have the day key, so they won't be able to make that much use of information. So, and then you set your wheels to the indicator, whatever that was, and then you come up with another random 3-letter combination. That's your message key, and you type that twice. Oh, twice. That's interesting. Then you set the wheels to that indicator, and then you send the rest of the message. So the idea is there's a message-specific key in addition, so that will sufficiently obscure things so that you won't be able to do frequency analysis. So that at least is the idea. And that's what the Kenngruppen at the right side of the code sheet that I showed you, that's what those were. You were supposed to pick, to use those for your random letters. Okay, so one of the things that Turing and others were able to do, this is about Turing after all, one of the things that he and others were able to do then is exploit human errors in the protocol, or errors inherent in the protocol itself. So for example, if these are the next 6 ciphertext letters in your machine, what can you say about it, and what does that diagram tell you? Remember the protocol. What does that mean? What do you know about these two letters? Anybody? They start with the same letter, or rather they represent the same plain text letter. That's information, that's useful. Similarly, the indicator tells you something about the relative position of the rotors. That's also interesting. But some of this is downright humorous. As you might imagine, these operators sometimes, they're tired, they're hungry, they're being bombarded, they're being shelled all the time. Having them pick random letters or shuffle through the code book to find the right ken group or whatever is tedious and boring, or it's stressful or whatever, it's just too much work. So they had operators who would pick their girlfriends' names and do that all the time. And so the Bletchley Park code breakers would often joke about, oh, here's Ingrid, or here's, that's the guy who's always doing his girlfriend's name. What other 6-letter word might be particularly popular, even though it's not 3 things repeated in World War II? Hitler, yeah, that was used a lot. Yeah, even though it's not 3 letters repeated, it was often the message-specific indicator. You could get a lot of information from that way. But the most useful thing for code breakers were cribs, what we now call plain text attacks. Many, many times you would be able to do, you could make good guesses as to what the plain text were. Jim, what's the first one? Can you tell? I grouped them into 5 letters, but you should ignore the spaces. Okay, so the first one, yeah, keine right? No changes to report. As you might imagine, there's a lot of that in Enigma traffic, because protocols said you have to post in at this time every day, and if there's no changes, you have to say that. So that turns out to be very useful. This other one is from U-boat commander von der Gruben. VVV was a standard for some reason. Wetterbericht, weather report. There was a weather station in Libya that, it's out in the freaking desert. What do you think their weather report was? No change, hot, dry, weather report, no change, weather, no change, et cetera, et cetera. The Allies, the RAF, was under specific instructions: whatever you do not bomb this weather station. Right? Because this is giving us cribs every day. Every day. It's great. It's great stuff. Okay, so in the movie you'll see, well, I'll mention this first. So for example, suppose that this is your Enigma text and you believe, and it's from that weather station. So you believe the crib contains Wetterbericht at some point. So where might it be? You're not sure where it's going to start. Well, did you try it at the beginning? What's wrong with that? It can't encrypt to itself, so that's no good. That one might work. Remember that for future reference. That one's no good. That one's no good, and so on. So in the movie, you'll see these big sheets with holes in it, and they move things around. That's what they're doing, is trying to line up cribs, plain text with ciphertext, and getting around, ruling out possibilities where the plain text letter and the ciphertext letter are the same. That's what's going on there. Okay, I'm going to skip this other part, maybe if there's interest afterwards, because I'm running out of time. Turing's particular contribution deals with the Stecker board, and how do you deduce the plug board settings. I'll say that it involves doing some logic and some reasoning and looking for cycles, and if there's interest afterwards, I can go through it, because it's absolutely fascinating, but just in the interest of time, I'll skip that. This is an example. If that's the Enigma receipt in the middle, and the crib was Attack at Dawn, I picked an English one, how could you make progress about the plug board settings? How could you do that? And it involves looking for cycles and then making some guesses and using the process of elimination. Turing designed and built a special purpose computer, really a hardware emulator for the Enigma, for multiple Enigmas. Each one of these things here represents a rotor, and for a 3-rotor Enigma, each one of these represents an Enigma replica, and the idea was to use this information to try lots of different possible rotor settings and plug board settings at the same time. You'd feed in the crib, and then you'd turn the crank, and it would say, this one can't be right, this one can't be right, this one can't be right. It was called a bomb because it would tick, and when it found a configuration that would match, it would stop ticking. The circuit would be open, and so that's why it was called that. And you'll actually see this in the movie. Okay. So why is it called the Imitation Game? Well, after the war, Turing continued to write and publish, and in particular, this is the paper where he proposed, this whole idea about whether or not a machine can think, that's sort of fuzzy and unsatisfactory. We need to really pin it down, and this is how I would propose you could answer the question. And he proposed what my colleagues well know as the Turing test. The idea is that if you are communicating via teletype with a machine or a human in the back room you don't know, and you ask questions and the answers come back, if you can't tell the difference, then we ought to assume, and it turns out to be a computer, we ought to assume that that computer is intelligent. That test is since now, I think, recognized to be flawed for a number of reasons, but that's referred to as the imitation. He called it the imitation game. It's now called the Turing test. And that is what, where that comes from. And that's what, this is how he calls it. Here is the scene where he is interrogated. So Turing, as I said in the poster, admitted to a homosexual relationship. He was not particularly closeted, but at the same time, he was a private individual. But he did admit to a homosexual relationship. This is after he'd been given the OBE by Churchill in a secret ceremony that, of course, he couldn't tell anybody about. His work and the work of the cryptographers at Bletchley Park are estimated to have shortened the war by 2 years and saved millions of lives. Here is the scene where he is interrogated.
Could machines ever think as human beings do?
Most people say no.
You're not most people.
He's being interrogated as a result of being accused of homosexuality.
Well, the problem is you're asking a stupid question.
Well,
Of course, machines can't think as people do. A machine is different from a person. Since they think differently. The interesting question is, just because something thinks differently from you, does that mean it's not thinking? Well, we allow for humans to have such divergences from one another. You like strawberries, I hate ice skating. You cry at sad films, I am allergic to pollen. What is the point of different tastes, different preferences, if not to say that our brains work differently, that we think differently? And if we could say that about one another, then why can't we say the same thing for brains? Just of copper and wire, steel.
And that's this big paper you wrote. What's it called?
The Imitation Game.
Right, that's what it's about.
Would you like to play?
So not really much subtle subtext there. I mean, it's pretty clear what that's all about. So I would like to wrap up. So I shall. Resume slideshow. There we go. Okay, so I did want to mention this wonderful woman who came and spoke to the cryptography class last year. Barbara Sachs worked at Bletchley Park. She's a veteran of the Blitz, and she lives here. She's 97 years old, and she's just wonderful. She's sharp as a tack. She's very British and just wonderful. I'll just put a picture of her up here. This is her, and there's a better picture of this. Is her in the actual cryptography class. She's just a real treasure. That's a picture of her when she was at Bletchley. And I just wanted to remind people that there are people like that living among us, and they're treasures. They're just wonderful. Okay, so just to wrap up. So what are the lessons from Enigma? The trade-off between security and convenience are very much still with us. And it's just a perfect example. And so it's important to be aware of that when you design your systems. You should design your systems with security in mind from the very beginning and subject them to rigorous mathematical analysis as opposed to just believing that they're secure. The protocols are only as good as the humans who implement them. So the best protocols are stupid-proof, and of which this one was not. We no longer regard ciphers that are vulnerable to plain text attacks as secure, and rightly so, for just this reason. It shouldn't matter whether you see the ciphertext or not. It shouldn't give you any information at all. Even if you know the machine and you know the algorithm, it shouldn't give you any information at all about the plain text. That's the ideal that we aspire to. What else? You shouldn't rely on the size of the key space as a guarantee of cryptographic security. The size of the key space, there are more configurations of this machine in theory than atoms in the universe, but it still doesn't make it secure. And I get this, and members, those of you in the Air Force who have ever been pitched by a crypto system, crypto is full of snake oil salesmen. I see them all the time, where people say, look, this crypto system is completely secure because the key space is enormous. It's like they pay no attention to this. Right? It's full of snake oil and people who take advantage of people who aren't necessarily mathematically sophisticated or who just don't really understand this. But I know none of my students in crypto, none of my crypto students, a couple of them are already here, will ever be taken in by that. So that's good. From Turing's life. So I believe that there are moments in history that are serendipitous, when just so many things come together and then amazing, big, significant things happen. I like to think America's founding is one of those moments, when just forces just converge, the right people, the right ideas, the right circumstances. And I think this is another one, when you had the mathematicians like Turing, but not limited to him, at just the right and the right resources, and Churchill gave them everything that they needed, and just the right people were at the right place at the right time to make things happen. Turing committed suicide. He was chemically castrated by his own government, despite all the things that we've been talking about. He took estrogen. He was made to take estrogen, which I guess was believed to reduce his sex drive or something like that. He grew breasts. He committed suicide by eating a poison apple a couple of years after he wrote that paper. There is some speculation that the Apple logo with the bite out of it is a tribute to him, but I've seen no evidence of that. I think it's just rumor. I haven't seen anything to confirm that. So, as I said up here, any suicide is tragic. Turing's life is a personal interest to me because, well, not only, of course, at how he ended his life. I had a friend who I went to high school with who was gay but closeted, many of us knew, and he killed himself a few years after graduation. The next generation, also gay, closeted, very clearly in a difficult environment with his family. And I went to his funeral, and I thought, this is enough. Enough. No more on my watch. And of course, I'm just one person, but I figured maybe by telling Turing's story, telling others, maybe over time, it wouldn't happen anymore. I just didn't want it. I didn't want to be around in a world where things like that happen, regardless of what you think about homosexuality. Surely we can agree that gay men and women shouldn't live in a world where they feel driven to take their own lives rather than be who they are. And so Turing's life and work were of interest to me, and that's a part of why I like to tell this story. Who knows what great ideas died with him? He died at a very young age. Who knows what we missed out? Who knows what other things we could have had as a result? Lots of acknowledgments. So there's lots and lots of books. I do want to particularly mention the National Cryptologic Museum, who has given us this on permanent loan. So this is an actual Enigma, which I hope everyone will come up afterwards and mess around with. You will find that it works in that if you set, and here's one stecker, but if you set the stecker and the rotors, you can actually even take out the rotors. I won't do that here, but you can at least look at it and lift it up and see how they work. But you'll find that it encrypts and decrypts exactly as expected. I apologize for running over so long. This is actually a work in progress, so I'll have to think about some stuff. Thank you all for staying as long as you did.